Thank you all for being here. Thanks for having me. Today I'm going to talk about some work that's now really like a little bit older, some on conformal interfaces. No, recently I moved on into sort of mostly studying holography for open systems, but since this is a workshop on interfaces and defects, I thought this is still a very appropriate topic. And I'm not sure how many of my collaborators talked in Europe about this, since we're mostly based in like Asia and the United States. So this is a workshop on interfaces. I heard you talked a lot about topological interfaces. So today I want to talk about conformal interfaces. So these are interfaces where there's definitely degrees of freedom living there. And we're having conformal field series, everything's gapless. Now understanding conformal interfaces presumably sort of a starting point for understanding all kinds of sort of defects and interfaces in quantum field series. I'm only going to be working in 1+1 dimensions. So the setting is basically something like this. We have a CFT1 on one side, we have a CFT2 on the other side, and then we want to have sort of an interface that preserves sort of the diagonal SL2R, like that's basically the 0+1 dimensional conformal symmetry. It's sort of a subgroup of the 1+1 dimensional conformal symmetry. Right? And you should know that this is the same symmetry as that of a conformal boundary. And for some reason, right, I think this is why people haven't really looked at these conformal interfaces all that much, because the idea is a conformal interface that's basically just the same as a boundary. And boundaries we understand really well, right? Cardi told us long ago everything there was to know about 2D CFTs with boundaries. That seemed to be like a completely well-explored topic where there isn't much else to say. But the first half is mostly going to be review. I'm going to tell you about a bunch of indications people sort of developed over the years that show that these 2D interfaces are really much richer, much more interesting than just 2D boundaries. There's a lot new to say about 2D interfaces that's just not there in the boundary series. And then I'm going to show you some of our main results is that we have some interesting new bounds on these new quantities. So first I'm going to introduce some new quantities. That's work of many people over many years. Some of this is us, but some of this is older, and I'm not going to be really good on references. But then I'm going to show you some of these bounds that we derive from this. Right? So there's two connections between this interface conformal field series, sort of ICFT, that setup that I described for you over there, where there's BCFTs. Right? So for one, you can always think of that the BCFT is a special case. Right? When I sort of basically choose CFT2 to be trivial, meaning like a gap theory without any degrees of freedom in the infrared, right? And clearly I'm back with describing just a boundary for CFT1. But there's also this general structure that I can have this mapping that any ICFT can be turned into a BCFT via what people call the folding trick. And that's sort of most easily to demonstrate with a piece of paper. Where if you have an interface, a conformal interface, I can always do this. And now the interface turned into a boundary for the product CFT. Right? So that I can basically say that the ICFT is basically just a BCFT for CFT1 times CFT2. People sometimes put a bar over there, but that's sort of saying CFT2 gets parity reverted. But it happens after folding, and now I have two CFTs living on the same space. Right? From that point of view, the ICFT is kind of a very special CFT. It's a CFT where in the bulk, away from the boundary, it's a theory that has two completely decoupled Lagrangians, and they only talk to each other along the boundary. Right? So that feels like a very special structure if you think of it as a BCFT, but it's purely geometric if it's really interface. Right? There's some sort of, in the real world, interfaces are everywhere, right? I will be describing the interface between two critical systems. In this case, the fact that the two sides don't interact is just locality, right? If I have one material here, different material there, of course, they only interact at the interface. And once I folded this over, I lose a lot of this intuition. So I'm going to define for you some quantities which are only natural quantities in the ICFT. I can still calculate them after folding, but after folding, they don't make nearly as much sense, because after folding, they crucially will rely on this factorization structure, which again is obvious. If I study an interface, it feels like artificial from the point of view of the BCFT. Yeah, if you classified all boundary states in like this product CFT, you classified all interfaces. That's right. So can be like, I think formally this can be an interesting device, this folding, but again, it misses a lot of the interesting physics in the sense that they're interesting quantities. I'm not sure how doesn't this do this best. How did you do this yesterday? Just like this? Is this like you sort of this one up and then I have to climb down? Okay. Like this. So right, there are new quantities in ICFTs. And one that I'm going to describe for you is going to be static. There's a new quantity that has something to do with entanglement entropies. There's a new quantity that's dynamically. And that's sort of about energy transport. Better. Let me start with the second one, right, where we talk about energy transport. And no, this is sort of an obvious thing that you can define when I have an interface where I have like my CFT2 and my CFT1. And if I contrast this with a boundary, so let me first do the case of a boundary CFT, right? In a boundary CFT, I still have time translation, symmetry, so we have a conserved energy. My momentum is clearly broken by the boundary since I no longer have translation invariance in the direction transverse to the boundary. But for this to be a conformal interface, it basically has to be a straight line on the plane, right? This thing is time translation invariance. I still have a conserved energy. So I can ask myself what happens if I send a wave of energy towards the boundary, and then if I have a boundary and energy is conserved, I know that everything I send in has to come back out. There's a transmission coefficient, or a reflection coefficient in that case, right? And the reflection coefficient is 1. Everything I send in on a boundary has to come back out. But if once I have an interface, I can set up a problem like you would do in undergrad quantum mechanics, where there's some fraction T of the energy that goes through and some fraction R which gets reflected. And because energy is conserved, the two have to add up to 1. But there's a new number there, right? There's a very interesting number there, which is a reflection coefficient. And you can, this characterizes the interface. There seems to be some universal number there characterizing the interface.
Under what circumstances is R equal to 0?
Okay, we can talk about this in a little bit more detail. So there, I'll tell you more about R. So there are examples where R is equal to 0. So in the Ising model, for example, when you can classify all these interfaces, there's three discrete families, which in addition have a continuous parameter. Ilka can tell you all about this because we worked this all out. And sort of there's an angle, and the angle goes from 0 to 1. And so for 0, the reflection coefficient is like the sine of the angle. The angle goes from 0 to pi over 2, and the reflection coefficient goes from 0 to 1 because it's essentially the sine squared of that angle. So there are continuous parameters which allow you to dial this.
R equal to 0 is only for topological interfaces.
Yes, it becomes a topological interface when R is equal to 0. But no, again, if you study the dynamical interfaces like in the Ising model, there tends to be like one parameter families where R equals to 0 happens at like special values of that parameter.
Yeah, the topological one is inside the big family of.
Right. So sort of, yes.
This angle's a bit like the kind of theta angles.
Okay, so if you fold, right, the Ising model, you fold it. It's two Ising models which you can bosonize into a free scalar, mod C2. So the interfaces of the Ising model are the same things as D-branes on the interval. And D-branes on the interval have the zeros on the 1 branes. If you think about the D0 brane, that has an angle which is the position on the interval. And if it's sitting at the edge, it's So the interesting thing here is there's old work by Quella, Runkel, Watts, Maineri, Penedonis, Russet, where they exploited this that this T and R hence are numbers. Right. If you teach quantum mechanics to undergraduate, transmission reflection coefficients in like wells and bumps, right? These are things you do all the time. And then you get typically the transmission coefficient as a function of wave number, right? That's the sort of thing you would calculate. For these conformal interfaces, the transmission coefficient does not depend on wave number. These can be as strongly interacting CFTs. They can have lots of nonlinearities. You might think it depends on the amplitude of the wave, depends on the wave number. doesn't depend on any of those things. T and R and the CFTs by conformal invariance alone, they end up being just numbers. So there's some very simple numbers that characterize the interfaces, and they're completely universal. Universal in the sense that they're independent of the excitation, right? They only depend on the interface itself. They do not depend on the particular excitation you choose to scatter off the interface. And I can use T. Not so far, right? There will be bounds on what R and T can be based on the sample cloud of CFTs. So I'm not going to talk. For interfaces, there should be a very interesting classification problem. Like if I hand you arbitrary two CFTs, can you find an interface between them? I don't have anything to say about the classification problem, but there are examples of CFTs with interfaces where the central charge is as different as you want it to be.
Can I ask a dumb question? Suppose your CFT2 was actually two decoupled CFTs,
yeah.
One of which actually had a boundary and the other one.
Right, so that would be simple, right? Simple example for like arbitrary big jump in central charge. This is even something I'm going to talk about like at some point.
The reflection coefficient definitely depends on what field you send in. Some bounce back, some go through.
So what we're relying on is there's a unique spin 2.
I see, as soon as they're coupled.
Yeah, so all the rigorous results that like Mineri and co proved rely on this fact that the stress tensor is the unique conserved spin 2 current. So if you have truly free series, there's always this sort of, now we have like multiple conserved stress tensors. So basically what you need is, you put, the way they calculate, you put an excitation way far over there and then calculate the expectation value of the stress tensor on the other side of the interface. And then their results rely on the fact that like the energy ended up all being like in the one unique massless conserved spin 2 current. If there are many, then it depends on which ones you're excited. Right here, you kind of what channel you send in, it stays in that channel. So in free series, there can be more than one transmission coefficient, but in, yeah, so the assumption was there's a unique conserved stress tensor.
Doesn't matter what the identity of the thing you throw in, everything.
Yeah, it's pretty fascinating, right? It's yes, I think it's cool. No, we calculated these things in free series quite a bit, and we had to grapple a little bit with this. The cool thing is in like the series we studied, supersymmetry, you might think it matters whether you send in a fermion or a boson, but then ended up it's the same anyway, so it didn't matter. So they have like in the free limit, you have both a conserved boson and both conserved fermion current, but you get the same transmission coefficient, so it ended up not mattering. Otherwise, you have to basically turn on a tiny perturbation that ruins all these free currents. All the conserved extra currents you have in the free series to know which one is the right one. Yeah, I'll come back to this example kind of very briefly later, the one with like n channels going to one channel. Basically, now this is where we're heading right now. This is going to be one of my examples where we already learned something interesting. What did I want to say? Right, so you can use T and R to define a new central charge. And here we call this C left right, or this goes back to earlier work. And you can read this off from, so say, the holomorphic part of the TT two-point function. But here the thing you do is you calculate a two-point function between a holomorphic current on the left and on the right. So this lives in the left half of space. This lives on the right half of space, and I should call them 2 and 1. That's how I called them before, right? And this has the standard form of like what a two-point function, a holomorphic two-point function should have. But there's some new coefficient C left right there, right? This is where the central charge, if you do like 2 with 2, you get the left central charge. If you do 1 with 1, you get the right central charge. But you get a coefficient like this between left and right, and this defines this new central charge. And now you can calculate the transmission coefficients. If you transmit 1 to 2, this is given by C left right over C2, whereas if you transmit 2 to 1, that transmission coefficient is given by C left right over 1. Right? And by using positivity of the energy flux, these are basically, they call this conformal collider bounds because Maldacena and Hoffman called it like this before when they did this in 40. By using this technique of just demanding positivity of the flux, we can immediately put a bound on the C left right. C left right is sitting between 0 and the minimum of the two central charges surrounding here. system, right? And what this is telling you, if you consider this case that we just talked about, say I have like one scalar on one side and have n scalars on the other side. If I want to calculate the transmission coefficient from 2 to 1, so this was 2, this 1, the transmission coefficient from 2 to 1, this is bounded by, I do this the wrong way. Okay, this is the 1, 2 to 1. This is supposed to be bounded by 1 over n, and the transmission coefficient from 1 to 2 is supposed to be bounded by 1, and this is Mesa Hammerstedt, right? The 2 to 1 is supposed to be bounded by the large central charge. No, it works. Yeah, it's good. Right.
Something in from the left.
If I send something from the left, it basically can get completely transmitted. Where something comes in from the right, right? So you can think if these are water pipes, this would make complete sense, right? If you have n water pipes coming in, n minus one of them end and can't go anywhere, so that has to somehow go back, but one water pipe goes through. So if you come from big central charge to small central charge, not much can come through. If you come from small central charge to big central charge, there's no limit. Everything can get over to the other side.
Your CFTs are non-chiral. C left is equal to C right in the usual.
I've not looked at chiral symmetries. There's like no. There's a student in Texas who bugged a couple of you with kind of saying we should do this for like. I think he sent you emails. I did. Do you remember Henry Makarov sent you emails and said he wants to? No, doesn't strike it. Henry sent you. There's somebody who wanted to do this and hasn't actually done anything along those lines. But
How can I relate this to talk of David yesterday where he had like such support section was 0?
Yeah, I'm not sure how this relates to that. I haven't looked at the chiral case at all. There might be something interesting to do for the chiral case.
But I was, it was 0 because it wasn't TT, it was a particular field,
But this can also be 0, it just means that it's a hard interface.
Under boundary state, I mean, examples of all such. What gets transmitted and reflected depends on what state you put on the.
Yeah, so again in the Ising model, you basically you have like a discrete parameter which in the folded picture is sterically where there's Neumann boundary conditions where it's the D0 and D1, and you have this continuous parameter which is angle, and then the transmission coefficient, the sine squared of that angle. So you can smoothly dial that through. But I'm not.
But for example, if there's cases where you do when you map things onto free bosons, when you turn it into a boundary condition, for example, Neumann is all transmitting in the usual conventions, Dirichlet is all reflecting. No, I mean it all.
Yeah, so some right. So there's some examples where there's no continuous parameters. Some it's like where they have marginal deformations that are living on the interface or not. So the most simple examples, free bosons, free fermions have free parameters. They have marginal boundary interactions. So you can dial T continuously.
The points both all transmitting and all reflecting are typically always conformal boundary conditions. There's
right.
In some cases there's intermediate.
So there's two examples which are kind of so trivial that I can do them in my head in like 10 seconds, and those are the ones I'm going to use for, most of what I'm going to, when I divide things for you. And one of them is what I call the no-brainer, or no, this is like Oliver, DeWolf, Friedman, Hofer, Aharoni, and I introduced this. And this is basically, you just have like a CFT, right? Sort of, you have a CFT that lives everywhere. You can declare x equals to 0 to be an interface. Why not, right? I can just say there's an interface here. Nothing's happening at this interface. In this case, C left right is equal to C1 is equal to C2, and the transmission coefficient is equal to 1. Right? Just kind of showing, yes, I can definitely saturate this upper bound. The other case is like two BCFTs. Right? In this case, obviously, C left right is equal to 0, and the transmission coefficient is equal to 0. If I have like two CFTs which don't talk to each other, that's the other extreme case where clearly there's no correlation between left and right, nothing goes across. I can have transmission coefficient that's equal to 0. It's clear that I can have the two extreme cases of like the upper bound and the lower bound, but my claim is I can have everything in between. They're very simple examples, free boson, the Ising model. So of the easiest examples where I can get every value between 0 and 1. Okay, so this was the first quantity that's sort of new in the interface, and we got out like some new central charge, right? There's something that appears like a central charge, it shows up in TT two-point function, and it characterizes the interface. So there's a new number characterizing the interface, some sort of effective central charge. There's the second number that I wanted to introduce, right? So this was my dynamical one. Let's talk about the static one. And for this, we have to talk about the entanglement entropy. So if I just have a CFT, there's this famous formula C is equal to C over 3 log L over epsilon plus some sort of constant. And okay, so that's sort of universal result about CFTs. And then for BCFTs, we were told we get like S being C over 6 log L over epsilon plus, and then we get some sort of log G, which in principle, right, so that depends on your scheme, because if I change epsilon, I change this log G, but at least differences in log G are meaningful, right? In this log G, people make a big deal of is the boundary entropy. So here's some extra number that seems to characterize my boundary for me, right? But once I have the interface here, I can define new things, right? Now I can study clearly interesting things should cross the interface, but I can have something like an L left and an L right, where L equal to L left plus L right. And there seems to be an extra freedom, right? There's basically the ratio of L left over L right is the new parameter I have in the interface. And now again, I can fold. Nobody stops me from folding. But this after folding looks like a very unnatural question, right? If L left is not equal to L right, we're saying basically integrate out everything, trace over everything that's out here, trace over half of the CFT here, and then trace over the full CFT in there. So that's a new quantity. These entanglement entropies that depend on L left and L right separately are new quantities which I can define for the ICFT, and they're not very natural after folding. They make a lot of sense only in this, if I generally think of the theory as an interface, not as a boundary. So right now we're doing this in the line. I'm doing this in the line, and I want to study sort of standard entanglement entropy associated to intervals. So it's a pure state, so it doesn't matter whether I trace either the outside of the interval or the inside of the interval, but and
you just move the defect around the interval.
Yeah, so the important thing is the interval crosses the, yeah, so that I have, right, I would think I have my interface is sitting somewhere, and then I take my interval and kind of where I send, right, I kind of move it asymmetrically across.
Constant there? Because you said there's an extra constant.
Yeah, so the constant, right? So then I would say.
Constant for the bulk and the boundary, or?
Okay, yeah, here people often don't write this constant, right? I can always say, I would say this log, there's a constant there, and that constant is interesting because even though it's technically scheme depends, the difference in this constants really teach me something. Sort of,
you didn't calculate this because there's this constant around.
Again, differences in log G make a lot of sense, right? If I go to a scheme where the constant is gone in the CFT case, now there's a constant that came by me putting a boundary there. I mean, it's just a fact of life that this constant is scheme dependent. So I fix my scheme, the constant becomes meaningful. Differences in this are meaningful, right? I can compare this. I can show that in a certain scheme by this G, I can also define via the cylinder partition function. Then I know what G I'm aiming for, and there's a scheme in which I get this, right? I mean, it's just the fact that there's an epsilon sitting there is telling me I have to be very careful interpreting the constants. But they are, I mean, people wrote like this G function has like monotonic under our G flows is like super famous. It's like the quantity to calculate a bounded boundary. But if I extract it from not from the partition function, but from the entanglement entropy, I have to worry about the fact that it's written, it's scheme dependent. Right, so this is what I write. If I make the constant so it's 0 here, then this is meaningful. Right, differences make sense if I do like with and without boundary. I get it.
That was my question. Whether if you use the same scheme for the bulk and the boundary, whether it's the same constant.
The interesting part is the new constant that appears there, right? Okay, so now let's talk about what happens with the. So let's talk about a few special cases, right? Sort of. When L left is equal to L right, then we are folding to a BCFT. Right, so then everything is kind of understood, right? If those two are the same, that's exactly the case when I get a standard entanglement calculation after folding, right? Sort of when L left is not equals to L right, and neither of them is 0, right? Then I get back the same answer. We're getting back that SE equal to C over 6, and C over 6 is C1 plus C2 over 6 log L over epsilon. Again, L is this sum plus log G. So this looks just like the BCFT, but the interesting thing that already happens here is that log g suddenly becomes a function. Instead of like a number log g, which was of the number characterizing a boundary, in the interface case, I get log g is like an entire function worth of data.
Isn't this first time C1 log L1 plus C2 log L2?
This sort of, they only differ by the constant, right? So you might,
You've absorbed that difference.
yeah, sort of, you can write this, right? Sort of, I can write this if I want a C1 over 6 log L over epsilon plus C2 over 6 log L left log L right over epsilon plus G tilde log G tilde L left over L right. And those two just differ by some there's some constant which depends itself. Right, this is a different function from this one, but it's uniquely determined. There's some scheme dependence in here, and this is sort of like, there are many ways, many schemes you could pick. These are sort of two very meaningful ones, because one, I think of it as two decoupled BCFTs, the other one nicely connects to the ICFT, but in the end, both just give me a well-known shift in this constant log G. So we wrote a paper in December where we haven't been careful, and we proved theorems about one of them and used it for the other and ended up in trouble. But by now it's fine. Or the revised version of this paper is fine. But one has to be very careful. There's like two very natural definitions of this log G, and you know exactly how they're related. But sometimes things are easier to prove in one case, and sometimes things are easier to prove in the other case. Now, we proved the theorem and then studied in the free fermion, or somebody else studied in the free fermion, and it was our theorem that we proved rigorously wasn't true in the free fermion, and then we picked up a third author in our paper, and now we're proving theorems that actually apply also to the free fermion. But sort of, yeah, so there's some very interesting thing that's already showing up here, right? We're used to log G being a number. Log G in the interface case is actually an entire function. This entire function, so it obeys something like a C theorem, but the C theorem as a function of its argument. This is basically, if you choose the right one, and I forget actually which one of those two, I think it was the G tilde one, that it has a derivative that's strictly negative. So it's only decreasing function of its argument. That sort of we can prove the same sort of, the same methods one uses to prove like that G, the number, decreases under our G flow. You can kind of use to prove that G, the function, decreases as a function of its argument. Sort of using either strong subadditivity to prove it like generically, or in holography, this follows from like positivity of the null energy condition in the bulk.
So the proof is purely within CFT?
Strong subadditivity I can prove for you.
But I mean, but meaning that you have to, in order to apply strong subadditivity, you have to define G using CFT, or? I mean, okay, let me, the subtlety is that there's lots of things that can be subleading in this expansion. Obviously, you can have subleading bulk terms that have nothing to do with the round. And Christian said, I mean, the way to remove those ambiguities is to take differences. So maybe that comes in here. But the point being, CFT then provides a nice, unique way, a universal way, if you wish, to define G. And then you can apply whatever you want. So you have
for strong subadditivity, all I need to do is I stick in this form and then I apply strong subadditivity. So if I assume my entanglement entropy has this form, and now I just.
So that's not then. You're saying this works for any G. So even if G isn't really a boundary thing, it's just the subleading. Because the point is G can have contributions both from the boundary and subleading bulk things.
No, I definitely need it to come from the boundary, because what's important in my setup is I have some intervals which include the interface and some intervals that don't include the interface. If I have enough time in the end, I show you our strong subadditivity cases. We're using a setup with Cassini inverter introduced first. We use some sort of boosted intervals which look something like this, and then we have our interface over there. And it's very important that I apply the formula. These two intervals pick up the log G with an interface, and those two pick up the log G without the interface. So it's,
okay, so it is important that G becoming solely from the boundary.
Yes. So it's that this G is the one that's the add-on due to the interface, and not the constant was the already in the bulk. Yes. So this is very strange here, that sort of you use the methods people usually use to study RG flow when you're kind of deforming the CFT, and you suddenly get now results within the CFT under deforming a quantity that's entirely defined within the CFT. It matters which side has the bigger LL. sort of you define this to be a quantity without loss of generality, you can choose LL to be less than R. So I think of this quantity always being something between 0 and 1, and then it's monotonic. If I flip it, obviously, it gets still monotonicity, but in the other direction. Yeah, we're doing the same. So all you need is that basically they are kind of in the causal development to kind of, right, that these, we're using the same boosted intervals, and you can still argue that because the boosted one is in the causal development of the other one, that they should still have the same central charges, same entanglement entropy.
Do you have a physical interpretation why this is negative always?
No. Let me get to my new central charge. So what I need is that these guys get logarithmic divergences when the argument becomes very small, and those are universal, and that I understand why. That's how I write something like this. The reason why I say I'm using the same techniques as I would do for like usually proving like RG flow evolutions. In the bulk, I'm just using the null energy condition. We're using the standard sort of what people would use to prove a holographic C theorem. Null energy condition, I'm proving that the warp factor has a derivative that's like sign definite. But the weird thing is that in these ICFTs, the warp factor, the radial direction flips. What looks like scale in the beginning suddenly turns into space, and I see how things evolve as a function of space rather than as a function of scale. If we ever get to talking about holography, this will make more sense. But yeah, sort of the standard techniques that you think usually tell you something about scale evolutions, these ICFTs end up telling you something about in the CFT how quantities evolve as a function of parameters in the ICFT. Okay. So something interesting already happens when I do this, but things get even more interesting when I take like extreme cases. And sort of the extreme case you might want to take is that I take L left to equals to be 0, right? Equal to 0. The 2 we see later. In that case, I find that the log term itself changes. SEE in this case will be, I still have a C2 sitting here, but now I get some C effective plus C2 over 6 log L over epsilon. Right? This is a new quantity. Yet another new central charge. I again call it a central charge because it's sitting exactly in the place where central charge is supposed to sit, but it's this time in entanglement entropy, but it's a different quantity. There's some old paper by Cardi and Calabrese where they saw this already, didn't do much with it, but you can calculate it explicitly in papers. Ilka calculated this for free boson. There's a C effective sitting there, and it's not either one of the central charges, it's also not 0.
What is it for a free boson?
There's the same parameter, zeta, on which the transmission coefficient depends. This also depends on it. Whereas the transmission coefficient is a sine squared, this is some sort of logarithm. It's some horrible, horrible, horrible function, which you never want to see in your life as a function of zeta. You can calculate it both for the free boson and the free fermion. The fun part is if you take a free boson plus a free fermion, it's like cosine plus logarithm for the one, and cosine minus logarithm for the others, and you get something very nice and pretty in supersymmetric series. But in free boson and free fermions, it's some horrible function. Again, you have the author who worked it out sitting there, so you can ask the whole about it better.
But it looks like it's got, because of the log L, it looks like it's associated to the bulk and not.
It looks like it, right? But it's not, right? It's a quantity that characterizes the interface, but it's sitting where bulk central charge is supposed to sit. Again, we weren't the first to discover this. I can tell you what it is holographically, and I can prove bounds on it for you.
What's the physical intuition there? To violate some locality.
Okay, so you might ask yourself, so right now I tell you something really special has happened when L left goes to 0. And what we, like last December in this paper that we wrote, basically what we show for you within holography, it's true that this log G develops a universal singularity when its argument goes to 0. And sort of you get a universal log singularity where when say I send L left to 0, right, then this can become as small as the UV cutoff, and L right becomes all of L. So basically what looked like a log G contribution suddenly makes it and becomes some coefficient of log L and looks like it's part of the leading log. But it's the fact that this thing has a universal logarithmic singularity. When I take that ratio to go to 0, that basically says in that limit is actually the coefficient of the log that changes.
Said differently, suppose I compute the entanglement entropy not including the interface. I get one number. I then move it epsilon across the interface, and I get another number, jumps discontinuously, but it jumps so much that depends.
So basically you get one number for the thing which you saw was the log term, but there's a constant there, and basically I'm telling you when you're kind of like you're doing this in the lattice, and you're one lattice spacing away from the interface, the thing that you called a constant actually itself is really, really large. And
the first time I wasn't even looking at the other side at all. So
you get sort of,
there's a constant.
even if the interval doesn't cross the interface, you still get the structure. Even if my interval doesn't cross the interface, the constant depends on the ratio, and the constant also blows up as I approach the interface. So if I do something like this, interface, and then like have like basically, I still would call this L left and L right. Sort of this is a function which kind of now I would call this like a negative L left, but you still get the same fact that G depends on L left over L right, and actually develops a logarithmic singularity as L left goes to 0.
Field, so this be saying that there's some singularity when the twist field hits.
So for this, people don't have a good replica calculation yet.
Might be like there's some fusion, some.
There may well be, right? So sort of if you do a replica calculation, the claim is Marco Maineri taught me that what I should say, what the C effective is basically that if you take the twist operator and have an interface in any boundary CFT, I can do like a BOPE, I can do boundary operator expansion where every bulk operator, and the twist operator is a bulk operator, I can expand in terms of boundary localized operators. And the claim is that the smallest dimension operator that appears in the boundary expansion of the twist operator, the dimension of that guy is basically given by C effective. So it's sort of the leading boundary contribution to the BOPE of the twist operator is supposed to be.
It's a bit like unitary CFTs that then the C function you have to move up by the vacuum energy, no? In some sense.
Maybe.
Yeah, no, in fact, I was going to try another piece of it. Yeah, the point is, if you change the boundary conditions of CFT, you can project out the ground state. And then what you think is C is really a different value. Now, that would be negative. Is the new central charge typically negative or positive?
No, it's always positive. So,
Okay.
so I'm about to kind of prove bounds for you on this, but
so in that case, then you're changing this. If you're changing the state of boundary versus state space and time, saying, well, we're putting something on the.
But I didn't do right entanglement entropies. I'm not changing anything, right? I'm studying the ground state of the CFT, and all I'm doing is I'm calculating different quantities. Yeah, right.
So get space and time.
But sort of no, the C effective only shows up for very particular choices of the. So if I calculate entanglement entropy for some interval that isn't infinitesimally close to the interface, it doesn't see C effective. And then I only see C effective if I make that probe, right? It's the property of this interval I'm choosing to calculate the entanglement entropy has nothing to do with the theory on the interface or the state of the theory, right? It's just some feature of the particular probe I'm using to study my theory.
So if the left-hand side is a completely trivial theory, it should just reproduce what you have for the boundary CFT.
Yes, then C effective is 0. Yes, C. I'm about to do my 2 examples, right? So since you asked me to, right, sort of in the no-brainer case, in the no-brainer, C effective is equal to C1 is equal to C2, right? Because in the no-brainer case, the coefficient is supposed to be C over 3, which I get when this is the same as this one. And then the 2 decoupled BCFTs, the effective is equal to 0, because then I'm supposed to get C2 over 6. Right, sort of 0 and full are easy to realize, but the claim is this is a coefficient which lives in the end we'll see between those two. Okay, things get even more extreme if I do the special case where I say take L left goes to 0 and L right goes to infinity, right? So now we are basically talking that I'm doing the SEE between left and right, right? In this case, you're getting that SEE ends up being C effective over 6 log L over X. No. Okay. So in this case, this is the different, maybe I use a big L, right? In this case, I get right, there's no more L, there's no more interval. I'm just saying, let me call my region A as CFT1, region A bar as CFT2. This is a quantity that's both IR and UV divergent. So I put an IR in the UV cutoff, I get a log of the ratio of the 2 cutoffs, and the coefficient is just C effective over 6. And this was our first place where we came in, because if you look at this, no, this is actually what sort of people, like when I say Ilka calculated C effective, this is what people actually calculated, because this is actually amendable to replica trig calculations quite easily. This is out of all the quantities, all the setups that we discussed so far, this is where you can just throw the replica trig at it, and if you're good at CFDs, you can get answers.
When you say that you use a replica trig, it means that we feel that it's C effective in the dimension.
In this, no, people just calculate partition functions. I think that this relation to the dimension that appeared, there's no paper where any relation of dimensions of twist fields to C effective has so far been published.
No, but it must be so, because C, like the normal result.
Okay, I should, like, did you, when you did your calculation, does this relate to a dimension of a twist field in any?
Our computation did not relate to a dimension of a twist field, but of course I don't know if like any other person kind of related this. So yeah.
I think it's my Neri to be published together with Elisa Grangameli, something like that.
I think I asked Marco Mene this, but probably it's true.
So I think there's supposed to be, no, Marcos understands exactly how this is related to dimensions of twist fields, so you should go talk to him. But I don't think there's a published work which relates the effective to twist fields. Even clearly it should be related, and some people know exactly how it's related. But this is where we came in. So if you look at the old review by Cardi and Calabrese, they basically introduced this as a different quantity from this one. They say there's some coefficient in this case, there's some coefficient in this case. We calculate them, they're different. And what we saw holographically is that this coefficient up here is just C2 plus this coefficient. There's really only one C effective. There aren't two different C effectives. And that you can actually show using the replica trig. When I say there's nothing useful we can do with the replica trig, no, with generic L left and L right, the one thing we've been able to do using the replica trig is actually prove rigorously that the C effective is the same as the C effective. I wrote 2 papers where we studied this in holography in more and more general cases, and then holography always seems to be true that the central charge is just this one shifted by C2. And then Yuya Kosuki at some point sent me this email, you know, I can actually prove this, are you interested in collaborating? And then that's how we started working with Roger and Yuya. Okay, so the upshot of all of this, and maybe one more case, since this sounds sort of this case of having both an IR and a UV cutoff looks kind of very artificial, this is actually all much easier to understand if you do this on the circle. Yes? Then you can fold, right? If as long as only in G, not in the, right? To see C effective, I need to have, so as long as both are non-zero, I don't see effective. To see C effective, my interval has to end on the interface.
Anywhere you see the impurity if we calculate the entire range with the symmetric case.
In the symmetric case, yeah, in G, right? I see it in G. Yes, the log G, the number. Then I'm back to having a BCFT where I say the impurity is kind of log G is the interesting quantity that characterizes. That's why I would call G the number, that's sort of the G people knew about. I have G the function, when L left is not equal to L right, and then I have G the number, which is when L left is equal to L right.
And the G the number, the usual G is you have to take both L left and the right to infinity or something like this. Just the usual one I would compute.
I mean, I would say it's a subleading coefficient sitting behind the log when I chose a scheme where, right, I assigned it some meaning, say, by saying the number is 0 in the case without a boundary. The circle, right? So if I do the circle, I have 2 interfaces, C1 and C2. Right now I can kind of make the following choices, right? I can study intervals which kind of live completely on one side. I can have intervals which sort of end on one, and I can study sort of intervals which go like from interface to interface, right? And this one will have a coefficient which is C effective plus C effective. The red one will have like C2 plus C2, and this is always over 6. And the green one will have C effective plus C2 over 6, right? What you're basically seeing is that these log contributions, these log UV cutoff contributions, you only pick up from the endpoints of the interface. An endpoint that's sitting in the bulk picks up the bulk central charge. An endpoint that's sitting on the interface picks up the interface central charge. And therefore this, right, this is the analog of this guy with the UV and the IR divergence. The one that's only C effective is the one which has all endpoints on interfaces, C effective at both endpoints. But this structure is completely modular. Right, this logarithmically divergent contribution to the entanglement entropy only comes from the endpoint of your interval. And then whether I see C or C effective depends on which endpoint I'm having. And if I do something that goes maybe one more right one that goes from the left to the right, that would see C1 plus C2. It's the log contribution is completely determined by the position of the endpoint of the interval, and no, C effective comes about when I have an endpoint, when I have an interval that ends on the interface. Okay, so the upshot is, am I on time? Okay, cool. I have 10 minutes left to actually talk about our results. I will not be forced to prove anything. I can just assert. We have till 11:30 with questions, and this counts already as having discussions. Okay, let me tell you our results. Right, so our main results are the following. There's a natural order to think 0 lesser equal to C left right, lesser equal C effective, lesser equal the minimum of C1 and C2. Okay. So I defined for you two new central charges that you only see in ICFTs, not in BCFTs, C effective and C left right. And for one, they're not the same, but they're still very important for each other in the sense that I can claim for you there's this universal inequality that C left right is always lesser equal than C effective, and both of them live between 0 and the minimum of the surrounding temperature. Furthermore, you can ask yourself, when is the inner relation ever saturated? And we are claiming it is only true when both of them are either the upper value or both of them are the lower value. I would be saying that basically this inner inequality is a strict inequality. The only time it's saturated if I have both cases trivial, right? If I'm basically in the topological case or the completely decoupled case. So let me tell you a little bit about the status of this, and then I can try to sketch some of these proof techniques. Okay. So the first bound, right, the one that involves C left right, that's the old one, that's Mainieri et al., where they use this positivity of the energy flux. So this we had nothing to do with. This was just naturally fits in this bigger framework. The bound for C effective, that C effective is also sitting in the same interval between 0 and the minimum of the two. This we can just prove. That we can prove using strong sum additivity. It's really easy to prove it holographically. So we had one paper where we kind of argued for you, just the same paper, but no, in the early stages of this paper, we saw it's true in free series. We saw it's true in holography. And that's for me pretty much good enough, right? If something's true at 0 coupling, something's true at infinite coupling, it's true, right? Obviously. But then we were actually able to prove it just using these boosted intervals of Cassini inverter. The other inequality we run between C left right and C effective, that one we are still kind of only at the stages. We can prove this in holography. You can check it in free series where kind of it's being calculated, and it's just this is the order to things. And again, if it's true at 0 coupling, it's true at infinite coupling. That's good enough for me. Good enough for me to write this like on a blackboard and claim this is a result. But this one hasn't been proven in like all generality. This one would be really interesting to prove, but we haven't gotten there yet. This is again where Marco is Marco is telling me he's about to prove it, but he's been telling this for like 2 years that he's about to prove it. And that would presumably involve this sort of relation to the twist operators. You can actually do something. The problem is that things are only defined via entanglement entropies. They're kind of hard to work with. You want to relate it to correlation function of some operators. You can go after it with some sort of more CFT techniques. Okay, that is actually, C effective in holography is about the prettiest of all of those, so I'll surely get to what C effective is in holography.
When the left is equal to the right,
yeah.
What is
So you mean when the CFT is the same, or when the LF? Yeah. So in the Ising model, C effective. It's in the Ising model again. Say do Ising model. That's sort of the easiest example. I can fold over. I get a D-brane on interval. I have a free parameters angle theta, and C effective depends on that theta as the tri-logarithm of the theta plus the cosine of the theta. So I can smoothly dial it all the way from 0 to a half.
So you can take a free fermion, for instance, with an impurity.
Yes, so there's a free parameter. If you want to characterize this impurity, there's a marginal coupling living on this impurity, and C effective depends on the value.
Because you see, when left is equal to right, the free fermion, I guess it will.
So for the free fermion, I was saying, right, 0 is less or equal than all this is less or equal to 1/2. The effective is there's a marginal parameter for a free fermion. I don't get like the interface as a marginal parameter. The effective depends on this marginal parameter. I can dial this marginal parameter for the effective to take any value between 0 and 1/2.
Those models I discussed yesterday, the boundary states have an angle, and for the rotor, you can add a theta angle for the rotor, which becomes the theta angle in the boundary states. So I think what you're saying is that this C effective should depend on the rotor theta.
Probably, and I mean, assuming that this is like the same as like the after folding I described in deep brains on the interval, gotta be right. There's a theta angle. If you have a theta angle and there's a theta angle, gonna be the same theta angle. You're using different language, but it's gonna. So, yeah, I think presumably that means if there's a marginal parameter, that's what you're telling me, and there's a marginal parameter for the Ising model, and the effective depends on that.
There are, I think for the rotor one, like this quantity is not constant because there's a symmetry of the bulk here that we move theta angle probably, like the vector of the axis.
I hadn't thought about that.
There are two cases. Either there is a symmetry or there is not, and when there is a symmetry, it's constant. When there is no symmetry, it depends on the. We wrote a small paper on this, but yeah, okay.
I haven't studied your case enough, but again, for the Ising model, I'm confident about what's going on. Learn from Kostas and Ilka.
Yeah, for sure.
And right, and also for the free boson, if I do the free boson after folding, I'm describing deep brains on the 2 torus, and they also have an angle. That angle is sort of, there has to be a diffraction of 2 integers, but it's kind of telling me like a p cycle, the q cycle that my deep brain is wrapping. I see that's sort of okay. Then so in that case, the effective is controlled by that angle, and you can dial smoothly between 0 and in that case 1, both extremes. Okay, so this is basically my result, right? This is what I wanted to show you. So we proved those 2 inequalities, where by proof we mean different things depending on which inequality. Right? In one case, we actually proved by at least by physicist standards. In the other case, we calculated in holography and in the free theory and found that answer.
Are there any statements you can make then about places where the interface is not a CFT? And so, you can get flows between different interfaces and all that, and are these things then possibly used to understand such flows?
If I study G, the function, rather than, so G, the number is monotonic under flows. If I study G, the function, you get some sort of weird statement that the RG derivative of G, the function, is bounded by the derivative of G, the function, as a function of its argument. So I can it's no longer sign definite. It can actually, G in principle can increase when a left and L right are very non-different, but the amount by which it can increase is bounded by the derivative of G as a function of L left over L right. So one can prove things, but they are not as useful, because sort of when L left is equal to L right, you can show that log G can only decrease under a G flow. And then in principle, it could increase a little bit at the edges of its parameter regime. But again, the amount, because it needs to stay sort of monotonic as a function of L left over L right. If it's decreasing very rapidly as a function of L left over L right, it can bend up under our G flows. But sort of the more it kind of bends as a function of L left and L right, the less constrained it is under our G flows.
What about C effective? No, I mean,
on C effective, we haven't been able to prove anything. No,
do a local deformation with defect RG flow.
One would hope that I have not been able to prove anything about C effective. The annoying thing is, right, in holography, you might think it's easy, but every time I try to prove something about C effective, so if I try to tell you that C effective is monotonic under RG flows, you end up proving this. And this is again in holography, the weighted direction in ICFTs turns into space, and suddenly you try to prove something in the RG flows and actually you end up proving something about spatial dependence on quantity. Okay, let me set this up in holography, since people seem to be asking a lot about holography. And that's the part of this I'm most comfortable with, so I'm happy to talk about it. So here's my boundary of AD CFT, here's my CFT1, here's my CFT2. here's my interface, right? And naively, you might write down some sort of radial direction, which you might call C, and then you would sort of write down my metric is something, but then everything you write here, you should think of as being a function of both x and c, and you have to solve PDEs, and you get a headache, right? Sort of, because I have in holography, everything always depends on the radial direction, but then because I'm studying interface, things will also depend on space, and this seems from the very get-go to be a hopeless problem, right? But things get easier because we're studying an I-CFT, right? And because of this I know that my bulk metric has to be writable in terms of ADS tools. And then I get a warp factor that only depends on this radial direction. We are back to solving ODEs. Right. Sort of, I'm slicing my ADS3 in terms of ADS2 slices, and this is basically, this structure is guaranteed to me by the symmetry that my interface preserves. So I know that my bulk has to be, everything has to be sliceable in terms of ADS2s. If I were to, right. So if I were to have empty ADS3 and ask myself how this ADS2 slice is sitting in there, basically what we're doing, instead of using Cartesian coordinates, you're using sort of spherical coordinates on ADS3. So this is the coordinate system we want to describe holographic ICFTs. You're naturally led to like a slicing like this, right? We are slicing the bulk in terms of ADS2s rather than slicing your bulk in terms of Minkowski 2s, which was sort of the standard horizontal slicing would be, right? In particular, like, sort of, right? I mean, there's some coordinate change between, right? This is my R goes like this, right? Sort of R equals to minus infinity would be like the left space, right? So if I want to study the boundary, that's R equals minus infinity, it's R equals plus infinity, which is sort of the right part, but then it's also like infinity on each slice. And so this coordinate system makes it very nice because it takes the asymptotic boundary sort of apart, puts like half of the asymptotic boundary at minus infinity, half of the asymptotic boundary at plus infinity, and the interface itself you reach by sitting at any finite R and then going to the boundary of the ADS2 slice. Right? Sort of, not just is this coordinate system dictated to you by conformal invariance, it's actually like very well suited to kind of calculate anything holographically for these ICFTs, because you nicely separate out where the boundary naturally falls apart into three pieces, just like you would like it to do.
Easier in the global coordinates, like they're just.
Oh, you can also say in global coordinates, the same slicing. Right, so whether this is global or Poincaré depends. When I write ADS2 here, now you get to choose what coordinate system you want to use for that ADS2. We always drew pictures like this, and then Taki Nagi wrote his paper about rediscovering BCFTs, and he started using this coordinate system. Right, it's just right. So here I draw this. Right, and then yeah, exactly. And this upper picture is like zooming in to there, right? I would kind of, this looks like this. And here my interface, right, it would have two interfaces sitting here and there. Yes, so I was about to give you 3 examples, and one of them is a top-down. So what do we have in examples? Right, so the easiest example is, again, is this no-brainer, the thing that sort of Friedman, Oliver, DeWolf, Ofer, and I used a long time ago to kind of make sure we're on the right track. And that's sort of when my bulk is just ADS3, right, because there's no interface. In this case, e to the a is just equal to cosh r. And if you just write cosh r, this is sort of this coordinate system with cosh r, I'm just describing ADS3. And what I want is basically, for any other ICFT, this cosh should be the asymptotic behavior, right? If R becomes very large and positive and very large and negative, my warp factor should go back to cosh. Right, so this is one example. The next example is RS, which I would call like it's a bottom-up model. Right? This is a model where I solve Einstein's equations, but I have to put in the sin sheet with tension, which, we don't have that in string theory. The brains in string theory solve dilatants and do all kinds of stuff, wrap internal cycles. If I just pull out of nowhere the sin sheet with tension, you can basically get something where I'm taking patches of ADS-CFT, right? I get sort of a cosh magnitude of R minus R star And then sort of have a brane sitting in R equals to 0, and my minimum move to R equals to R star. Right? So this is RS. People use this to calculate all kinds of things because it's sort of so easy, because everything.
What's the gap on
I mean, this is glued together. Sort of what's happening here, the metric is smooth. I glued together two spaces which don't fit together. I made sure that the induced metric on the brane is the same, but it's the relative mismatches, and that's this Israel jump equation. The extrinsic curvature doesn't fit, but the metric itself fits. I can even have different cosmological constants. Right? This is bottom up. You can do whatever your heart desires. But yeah, this is like people calculate a lot with this again, not because it's like very useful, but because it's so easy.
There's a tension of the brane which depends on the
This angle, right? There's some angle here, and that angle is set by the brane tension. And yes, the C effective doesn't actually depend on this. The RS model is kind of very bad because the effective is always equal to the central charge in the bulk in the RS model. But since you asked me about top-down, right? What's the easiest top-down model? The easiest top-down solution is the Janus solution. Right, so you basically take ADS3 times S3 times T4, right, which is dual to like this, symmetric orbifold of like E4 to the n's mod Sn CFT, and you turn on the dilaton. So you have like phi being some function of R, and you solve Einstein's equation, you find that e to the a is, I need to look at my notes for this because I didn't memorize the metric for Janus by heart. But here we go. E to a is given by a half square root 1 plus square root of 1 minus 2 gamma squared, where gamma is a free parameter, which is telling me, right, so this gamma is setting like phi at infinity minus phi at minus infinity, right? You might ask yourself, why does the dilaton move to begin with? I specify the dilaton is constant here, and the dilaton is equal to a different constant over there. So these are the boundary conditions I throw at that. And I have a parameter gamma, which is telling me how much different is the dilaton on the left and the right. I get a metric depends on this parameter gamma, and then it becomes just a cosh of 2r. Right? If you were to draw this, this is the cosh, and then Janus looks something like this. It's kind of a slightly stretched cosh. Right? If I give you one of those warp factors, you couldn't see whether it's Janus or empty ADS3. If you once you plotted empty ADS3, see that Janus is a little stretched, and maybe I didn't draw this well because one important thing is that Janus goes a little further down at the origin. Right, the cosh, the minimal value of cosh is equal to 1, whereas the minimum value of this one is a little below 1. Right, it's where if gamma is 0, this is a half 2, which is equal to 1. If gamma is non-zero, the warp factor drops down a little bit further than 0. So I would say the generic, the picture for the generic ICFT. So the minimum value, right? The minimum value is when this is equal to 1, and then it's like a half 1 plus square root of 1 minus gamma squared. So if gamma is 0, then the minimum value is still 1. If gamma is non-zero, it drops down a little bit. Gamma squared is bounded from above. So gamma is between 0 and square root 2, 1 over root 2. Yeah, I think this is the way this is parameterized. If gamma reaches maximum value, this is basically when my phi takes, like when my e to the phi would drop to like 0 or something like this. Let me draw a picture and we can talk about this top-down example a little bit more detail. Right, so the generic picture is basically, I would be saying I have sort of a space-time where there's like a region where I'm not ADS3, and I'm ADS3 here and ADS3 there. Right, so this is how the generic smooth solution would look like. I turn on some energy density, and the energy density will deform my space-time sort of in the middle, and then asymptotically it goes back to its ADS3 form.
In this case, the CFTs have the same central.
Okay, so what is in this case? Right, in this case, my CFT on both sides, right? I would have C1 is equal to C2 is equal to the same central charge. And in both cases, I have the symmetric product on both sides. But what changes is like different T4 radius.
It's a big modulus. Just
So there are many scalars in the bulk. I picked one of them, which is the size modulus of the D4, and made sort of I'm describing this D1, D5 system as slightly different radius from the left and the right.
Looks unlikely from this picture, what you said previously, the transmission coefficient.
The transmission coefficient is independent of the excitation in this case. We calculated transmission coefficient in this, and it's completely independent. Sort of in ADS3, my graviton is basically only skimming the boundary, the graviton. So in the bulk, in bulk, with the calculation I'm doing in the bulk is a graviton wave scattering calculation. You have a gravitational wave coming in from the left, and you're calculating transmission coefficients for the gravitational wave. And that gravitational wave is basically, right, it's a boundary graviton because I'm doing it.
Suppose I sent one of the other bulk fields through. Then doesn't the energy depend on where it lies in the radial direction?
The graviton, it's...
Not gravity. Something that can really propagate throughout ADS.
Right. Okay, then I have less of my understanding of why this should be, but in the end I think it will... Right, I'm calculating energy transport. In the end I'm only interested in graviton, right? I'm interested in the transmission coefficient for the conserved spin 2 current, yeah. Like other fields might have their own transmission coefficients, but the energy transmission coefficient is the one that defines this universal. Yeah, they did that, yeah. So that bulk calculation has been done by Costas and co. It's definitely special to ADS. No, I have two students who've been also working for like way too long on trying to set this up in higher ADSs, and we still don't know the gravity. So if you want to have something interesting to do on the gravity side, scatter gravitation waves in ICFT in more than 2 dimensions. I still don't even know whether this universality is still there. What does the answer depend on is still a very valid question. In conformal, there Per Krause and his students did a calculation for free conformal field space in arbitrary dimensions, and it's still true that you get these universal answers. But I'm not sure if it's sort of like, because I did a free calculation, or is it still true that transmission coefficients in higher dimensions only do not depend on any details of the excitations. It's true in free conformal field space, even higher dimensions. I don't know about the gravity calculation. The calculation has been done is in ADS3, and the techniques being used rely heavily on ADS3, right? I don't think there's a strict statement that it's not true in higher dimensions, only like whatever they did doesn't work in higher dimensions.
I didn't know about the Per Krause, so how do they define transmission and reflection?
I mean, again, it's a free scalar calculation. You can write down a free scalar, say here's the boundary conditions for a free scalar. You can write down here's the calculated transmission coefficient, which depends on all kinds of stuff. Then they say, now let's do the local special case where this is conformal, and then everything drops out and it only depends on the coupling constant. In that case, it's sort of the transmission coefficient for the scalar itself, I think. It's more or less the same for the, right? If you have a single free scalar field, things get only transmitted because the scalar gets transmitted.
I think in the paper of Medieri, Madonna said that one of the reflection coefficient, they kind of took this in 2D that doesn't depend what state you put as long as you scatter like
right. All techniques people use to prove things rely heavily on the 2D setting. It's probably it may not be true in higher dimensions. The one example where I know people calculated things, it still happens to be true that it's independent, but again, that's sort of a free scalar. That's sort of not even I would go so far to say things are true for a free scalar, therefore they're true in any CFT. Right? Free scalar plus ADS, that's good enough for me, but just free scalar, it's kind of maybe a little too special to kind of draw strong conclusions from. I wanted to get to C effective for you, right? Sort of what's the simplest definition of C effective, right? Sort of C effective, one place where we saw C effective was this limit where we send L right to 0 and L left to 0, L right to infinity, right? Where we calculated the entanglement between the left CFT and the right CFT. What's the RT surface in that case, right? This is something probably everybody in this room can answer in like 2 seconds. The RT surface, that when I say this is A bar, what's the RT surface? So I want an RT surface, a minimal surface, and ends on the interface and doesn't have any other boundary out there. Right, it's the vertical line down. Right, so that's the RT surface that defines the effective for me. Basically, what you read off from this is that the effective is given by the radius of the smallest ADS2 slice. Basically, like for the Koch, it's 1. For like ADS3, the smallest ADS2 slice has the same curvature radius of ADS3. And in Janus, it's a little smaller, right? And the fact that this warp factor for Janus is lying below that of empty ADS3, that's exactly saying that C effective for Janus was below the value on the CFT. And you can use the null energy condition. You can show that if the null energy condition is obeyed, C effective is always, right? The curvature radius of the central ADS2 slice is always less than the curvature radius of the embedding ADS3. And this goes back to sort of part of the heart of what I was trying to say before, right? Sort of if you've read the early papers in ADCFT, right? First year after Maldacena came out, like Friedman, Gapser, and some others proved this holographic C theorem where they show null energy condition in the bulk guarantees that A, the derivative of A has a certain, A double prime is negative. So you might say, great, let's do this here, right? So we can use the null energy condition to prove some derivatives of the warp factor. So I can show that the warp factor, it's not as easy as decreasing, but here you get basically the null energy condition is telling you something that A double prime is less or equal e to the minus 2A. That's what you get out of the null energy condition. Then what you do is you define some quantity which is sort of F is basically A prime squared plus e to the minus 2A. And then you can show that this thing has a derivative with a sign definite. But the real thing that's happening is you try to prove something under RG flows, and this R coordinate, this radial coordinate, which started out being scale near the boundary, suddenly turns over and becomes space as it crosses the interface, right? And then, yes, you can prove that A does some sign definite thing, but all what you end up proving is that the curvature radius of the central slice is always less or equal than the curvature radius of the asymptotic region. So instead of understanding how things evolve under RG flow, you instead prove the statement that C effective is less than the minimum of the surrounding central charges. So, and that happens every time you try to do something with RG flow, because even so now I love this coordinate system. I wrote this like, one out of 3 of my papers used the coordinate system. But in the end, it's kind of very unuseful if you want to prove things under RG flow, because it kind of divorces scale from radial evolution in ADS3. Right? Because it turns around this R coordinate, somehow mixes up space and scale. Not,
When you say RG flow, you mean boundary.
Right. So you know, standard ADCFT, you want to study scale evolution of the boundary. In ADS, you want to see how things scale with radial direction. But then this radial direction that naturally rises in the ICFT settings isn't really scale, right? This R coordinate is a radial coordinate in this particular slicing, but it doesn't nicely map to scale in the CFT. It's some combination of scale and space in the CFT.
In general, I always found it difficult to insert it at scale. For instance, you have to put a black hole there.
Right. I mean, people did it. So there's like the Janus black holes, Bach, Goodperl, and Hirano worked them out, but then you're back to solving PDEs. Right? This coordinate system, basically, you're starting a problem that really should make you solve PDEs, because things depend on the radial, on the bulk radial direction and on the spatial direction of the CFT. And it's a conformal invariance that somehow saves you and turns it into an ODE. The moment you do anything that breaks scale invariance, you have to solve PDEs in the bulk. Right? There's no, this is sort of a string theory attitude. Oh gosh, I have to solve a PDE, therefore it's an unsolvable problem. It's not like solving PDEs is the end of the world. People do solve PDEs all the time, but you can no longer get away with just putting like D solve in Mathematica and getting an answer. You actually have to do something. Again, the black hole, since you mentioned it, that's a solved problem. There's sort of a solution for the black hole in the 3D Janus that has been found. The finite temperature version of this particular top-down construction, people do have an answer for. So the warp factor itself isn't monotonic. It's this thing F that's monotonic, A prime squared plus e to the minus 2a. And that's sort of why if I go to the boundary, e to the minus 2a vanishes, and I'm picking up the boundary radius. At the maximal slice, a prime vanishes, and I'm just picking up e to the minus 2a. But in between, the warp factor doesn't have to be monotonic. There are examples where a has multiple minima. Then I would say, for me, C effective is sort of the smallest of all of those. But then basically you get sort of RT surfaces which are local minima but not global minima. And what those mean, there's a paper by my student Mianchi together with Christoph Uhlemann where they try to interpret these other saddles. So there are interesting features, these ICFTs and BCFTs. No, the gravity duals for ICFTs can have very interesting features, but yeah, it's not as simple as being monotonic, but it's the fact that this F function has some sign definiteness is enough to prove that one statement that we wanted to get out of this, that C effective is less or equal than the minimum of C1 and C2. To get the transmission coefficient out is actually hard work. No, that's sort of where Costas, this is sort of some interplay. Costas did it for one brane, then my student Saba and I did it for two branes, and then Costas went back in and said, well, if I want to do some arbitrary smooth function, we have no idea how this works. This is actually a major embarrassment, right? Sort of, this should be a simple enough calculation, just 3D gravity. People still don't know how to calculate the transmission coefficient for anything other than Randall-Sundrum branes, right? Randall-Sundrum branes are nice because I'm really doing just gravity waves in pure ADS3, and they're purely surface waves. So what Costas does, he takes any space-time, and he basically, if you have some sort of smooth energy density, this is my bulk energy density, he chops this up into a bunch of delta functions. And then he says, what I'm doing now is many Randall-Sundrum branes, right? And then in the end, I can take this limit where I take all these delta functions to 0. And that's the calculation that's basically been done. And one shouldn't have to do this, right? One shouldn't kind of, if somebody hands you a geometry with some smooth energy density, your first reaction shouldn't be, let me chop this up into lots of Randall-Sundrum branes to make like Lisa and Raman happy. And now I calculate the transmission coefficient. That's the only way for me to go back to the smooth energy distribution. In the end, you get some super simple answer. You get just that basically the transmission coefficient is in proportion to this integral of e to the minus 2a. But the only way people get there at this stage is by using it. If you calculate the gravitational wave, it's basically the constant plus integral of e to the minus 2a. It's sitting right there, but people still don't know how to extract the transmission coefficient. And every time I talk to Costas, it's got to be so easy, but no, it's like, we've been stumped by this for the longest time. Now there's an answer, and I believe there seems to be nothing wrong with this, right? It gives me an answer. It seems to be the correct answer, and I can tell you some more why I strongly believe it's the correct answer. But there's no sort of calculation of this using the smooth geometry itself. It has to, people go via this detour of chopping up into lots of Randall-Sundrum branes. Now, what Saba and I saw is that if you do two branes, basically all that happens as far as the transmission coefficient is concerned, you just sum the tensions. And you can even have like, can have 3 different cosmological constants between two branes. In the end, you just sum the tension. And Costas went, well, if you do this, in the end, the answer is you just sum all the heights of all these delta functions. That gives you the transmission coefficient. Right? That's what this integral in the end ends up being. There's some sort of effective tension. You just sum the tension of all the RS branes. Okay, what do I want to do? Since we talked about this holographic settings, right? I'm not going to show you anything about this transmission calculation, especially if Costas was here already. So Costas told you how to calculate this. Yeah, then I will not even try. Right? That would be an entire talk, and I wouldn't want to give it because it's a much more difficult thing than anything I talked about today. But let me talk briefly about supersymmetry. Right, so Janus, there also exists like a SUSY Janus. And that's been written down by Michael Gutperle, who's been here, right, apparently a few weeks ago, and then John Estes, Eric Doker. They wrote down supersymmetric versions of the Janus solution. The problem is that the SUSY Janus they look like ADS2 times S2 times S2. No, there was only one S2 times T4. And then you see this adds up to 8. There's some sigma, and basically what's happening here, the R symmetry in the supersymmetric case gets broken to SU2 times SU2. In the non-supersymmetric Janus, you can preserve the full R symmetry. In the supersymmetric Janus, the R symmetry gets smaller. So Janus is one of those examples where the more supersymmetry you add, the harder the calculation gets, right? Because the price you have to pay for more supersymmetry is less R symmetry. As far as gravity is concerned, having more supersymmetry, less R symmetry makes life much more difficult. In this case, like this warp factor depends on two coordinates, the two coordinates in this Riemann surface sigma. Basically, what's happening is to preserve supersymmetry, the warp factor has to depend on one on the internal directions of the S3 as well, right? That's sort of what's going on there. So it takes sort of, it's a real tour de force writing down the solutions, but they've been written down so you can work with them. So in this case, what you can do is you can calculate G, C effective, and C left right. You can calculate them in the free orbifold CFG. And you can calculate them like in the Janus solution. So this would be saying infinitely strong coupling where supergravity is valid, right? You took this orbifold CFT and you blew up all the singularities by a very large amount, or you calculated them in the free orbifold CFT. And they're exactly the same, right? There's seems to be a whole new slew of supersymmetric non-memorization theorems that show up if for all these interface-related quantities. There's absolutely no dependence on this bulk marginal coupling constant in any of those quantities. So this one and this one had been calculated by Michael Gadpal a long time ago, and we calculated this last summer by using the transmission coefficient from the 83 calculation and calculating the free conformal field theory. And this one, there's a paper with Miyanchi and Hiroshi where we used a sort of old supersymmetric water identities in 2-2 series where we can prove that G doesn't change. And the main reason for this is G has a very nice CFT definition, which was also Ilka wrote down with her friends in terms of Calabi's diastasis or something like this. You can write down what G is, and then you can use this to prove that in the 4-4 theory, G actually doesn't change, but I still can't prove that those two don't change. But I can calculate, right? I can calculate those numbers at weak and strong coupling, just happen to be the same. If I do the non-supersymmetric Janus, they disagree.
They disagree. Yeah. Okay, so it's really
in the non-supersymmetric Janus, this Takiyanagi and I calculated this 20 years ago or so. It was like no good motivation and kind of nobody dealt with this, and then we recently came back to this, but no, this differs, and also the transmission coefficient C left right. Saba, my student Saba and Sanjay Chashi calculated this both at weak and strong coupling and also disagrees. I'm not sure how much, so our proof actually needs the full 4-4 SUSY. So I'm not sure how much SUSY one needs, but with 4-4 SUSY it's true, and we can prove, and all seem to be true with 4-4 SUSY, we can only prove this one. No SUSY, they're definitely not. 5 more minutes. Need to make choices what I want to tell you about. Maybe I'm not going the strong subadditivity. I told you about supersymmetry. Maybe this is probably strong subadditivity is sort of the only interesting thing that's still left to say. So let me contradict myself and tell you about strong subadditivity. Right, sort of how to prove anything. Oh, do you have more questions for 5 minutes since I only have like 90 minutes in total? Maybe do questions. Okay, this is the sort of question where like nobody has done any, like that would be nice if one could do something. I don't think people have done a localization calculation of which one of those, right? Sort of one is like a TT 2-point function, the other one is defined by entanglement entropies. Neither of those seem to be an object that's sort of very amendable. Yeah, so G is the one that's easy to calculate. Can I do a localization calculation for G? I mean, G is the one people already have a lot of control over. I'm not sure whether we need more techniques for G. It's the other two that are kind of.
The other two you can, okay, the C effective, maybe you can do something on the torus, no?
Maybe with like supersymmetric Rayleigh entropies.
Be my guest. No, it would be nice to prove more, right? This is an arena where clearly lots more can be done. We just scratch the surface and.
Yeah, but I guess so. The C left right, no. There is, if you take two CFTs, no, you take T left and T right. There is a doublet. Or there is the first tensor T left plus T right. Is this W operator, no? It's T left minus T right, kind of, no. And C left right is kind of is 2-point functions, right? I know. That should be something.
Right. So because I know left is left, and I know right is right. So left with right is the only new thing that would show up, and T left minus T right is 2-point function. Yeah, good. So
good primary, but that's in some SUSY multiple. So probably the SUSY structure kind of gives you this C left right. That's something else simpler.
So for the log G, what indeed happens is that log G only depends on sort of the group element, right? Sort of I have two different points in the conformal manifold. In the end, G only depends on the group element it takes me from one to the other. It doesn't depend on where I'm actually sitting in the group manifold, but only on like how much I'm moving on the group manifold. It's sort of the distance on the group manifold is basically log G. But we didn't and that allows you to sort of prove things. Right? Did I drop my mic? No, you dropped your phone, I think. But if I'm sitting somewhere on this conformal manifold, then I can sit like a strong coupling and then if strong couplings up here and weak couplings down there, I can move the same thing down there and I get the same answer for log G. But no, unless you have something like this, I'm not sure how to prove things about the effective. This is sort of Hiroshi and Miyanji are still working on this. I decoupled because this they left me in terms of like using sophisticated like techniques from the 90s about like TT bar equations, yada 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 yada. But so far nothing has happened there yet in terms of proving things about the effective or C left right. You still want to hear about SSA, or you want to be done? Okay. Right. Sort of, if we want to, the thing we actually prove, right, where we prove something, this was this Cassini-Herder setup, where you're trying to use a strong subadditivity, and you're using a setup where you use these boosted intervals. So this is supposed to be a light cone. I have A and B and C. Right, and the important thing is if I arrange them in this particular boosted way, then you can arrange it so that D, right, D I can think of, sorry, this is D and this is A. D I can think of as the union of B and C, and A I can think of as the intersection of B and C, right? And the important thing is that of the intersection of B and C I can causally evolve into A, and D I can causally evolve into the union of B and C. So therefore I would think as far as the entanglement entropy is concerned, D and the union of B and C are the same, and A and the union B intersection C is concerned. In addition, I can arrange this in such a way that the length of A times the length of D is the length of B times the length of C. So this particular setup of boosted intervals it's a very useful thing for proving theorems. And then the strong subadditivity, this universal property of any entanglement entropy is that the entanglement entropy of B plus the entanglement entropy of C has to be bigger equal than the entanglement entropy of A plus the entanglement entropy of D. Yeah. The entanglement entropy of B plus C is bigger equal than the sum of the entanglement entropy of the union plus the one of the intersection. So that's a universal property of any entanglement entropy in any setting. And if I apply this to this particular set of boosted intervals, Cassini and Herder uses to rederive the standard C theorem, right? You can use this sort of simple inequality to derive sort of the same theorem people knew already is true, but you can derive this from a simple entropic setting. And if I apply this in our case, basically our result on C effective pops out almost immediately. And that's because if you look at this is sort of a proof I can even do on the board. Yeah, this is kind of unfortunate. I just made it go away. But so the important thing is if I put the interface here, if I put the interface on this end, then you see that D has the interface and B has the interface, but A and C don't have the interface. So I get out of these four intervals, and this was the question we asked earlier, right? It's really important that two of them touch the interface and two of them do not touch the interface. So if I write down what I'm having here, I get 2C1 log of B plus C1 plus if C effective log of C. And now these are like the lengths of the intervals. It's bigger equal than 2C1 log of A plus. Okay, I can draw AB. I can draw this again. How about this? Let me quickly draw my intervals again. I have these two light cones and I have like D. This is B, B, A, right? Something like this. So I have like B plus D is bigger equal than A plus D. And then I have to plus constant. We should be honest and drag this around. Sort of B plus D is bigger equal than A plus D. And the important thing is D, and okay, I actually did it the other way around. B, C. D and C picked up a C effective, whereas B and A don't pick up C effective. Right? So in addition, we have that log A plus log B is equal to log B plus log C. So that you see that the terms, there's a universal term log with C1 is like log B plus log C equals log A plus log D. So I can drop out this log A does not touch. Yeah. Yeah, that's why I have a 2C1 here, right? Yeah, that's sort of hiding in my plus constant. Okay, so I'm about to sort of right. There's something that depends on the ratios. Let me tell you what I'm about to do with this constant of how I make it drop out, and then it's basically I'm demanding a particular property of this constant in a certain limit. It doesn't have the epsilon in there, but that's maybe not good enough. So these are sort of this is okay plus some function plus reminder. Okay, so where we're heading, so right, if I drop out, so this allows me to see the C1 terms, I can just drop universal from everywhere, right? Because the C1 terms on the left are equal to the C1 terms on the right. So then I collect all the remaining terms, you end up with C1 log B over A bigger equal to the effective log B over C plus this remainder. And no, log B over A and log is, right, this is the same as log B over A. And so what I need is that I take this limit B much bigger than A and needed the remainder. Okay, I don't want that there's any singularity in this remainder as B becomes much bigger than A. And that should not be a problem because this remainder only picked up infinities when I made something like intervals, right? They're logged, this remainder blew up whenever I got like something very close to the interface, and I don't do this here, right? I can make these log terms very large, and so I can neglect the remainder, and then you're immediately left with C1. Now I have the inequality. Oh yeah, no, this is correct, right? C1 bigger equal than C effective. And for this, I kind of put this Cassini route on one side. I can also do it on the other side, and I can prove C2 is bigger equal than C effective. And if C effective is less than both, it's less than the smaller one of the two. So you can say that this is sort of, if I told you it's a proof, right? So I need to kind of, right? I call it a constant, and I need this constant too. We want to take this limit B much bigger than A to drop that constant. And when we wrote this, we just called it a constant, but now I understand it constant a little better now. And you need to you need that it doesn't blow up in this limit when I take B much bigger than A. That these terms become arbitrarily large and this one doesn't. They do something different, right? It's the same setup, but then they do something very different. I do something, right? I think this is much easier than what they had in mind because they wanted to mimic a derivative. So they do this like this sort of, they want to have that, so the difference of two entanglement entropies of intervals that are extremely close, they can do derivative. I don't need derivatives, right? I use the setting as it is, and the limit I want is that B, right? It's sort of B much bigger than A, which is the same as D much bigger than C. So this is just a statement about what I do with these intervals far away from the interface, right? This remainder blows up when I get within like if I have ends of my intervals very close to the interface, and we're exactly not doing this. These lengths are supposed to be maybe I don't want to say anything that you later tell me is wrong, but I need the length of D to be much bigger than the length of C, and length of B much bigger than length of A. Right, I want this inequality I want to be dominated by the log terms. Need to drop this, and then the inequality is sitting right there. Yeah, that sounds good. I think said everything I wanted to say.